So we're going to look at an example in this video of an actual Riemann sum approximation. So let R be the region bounded by the graph of f of x equals x squared plus 1 on the interval 0 to 4. Here, I should clarify one thing when we say this region bounded by the graph of f of x equals x squared plus 1. There's really kind of an implicit added part to that where it's bounded by that function and the x-axis. The x-axis. So we're looking at the region between our f of x and the x-axis. So the first thing I want to do is just look at this interval. I want to get a clear picture of what it looks like. And your sketch doesn't need to be super precise, and mine I'm not going to label every single point, but I want an idea of what this region looks like. So if I were to graph x squared plus 1, I have the graph of x squared. All this plus 1 is going to do is move my vertex up to 0, 1, rather than having our vertex at 0, 0. So our vertex would be right here. And I have the graph of a parabola. I'm going to kind of pretend like I'm zooming in really closely on the x-axis. I'm going to exaggerate my features just because it's going to make illustrating some of the next parts a lot easier. So I'm going to say, okay, my parabola, I've got a horizontal tangent line there. Perhaps it looks something like this. And we want to go from 0 to 4. So let's say here's 0, here is 4, and actually let's just move it over just a smidge. There we go. And we're looking for the region in between our function that we've just drawn and the x-axis. So we are looking for what is this region right here. That's what we're trying to approximate in this problem. This is the region R. So I would like to estimate this region using Riemann sums. It's the only tool that we really have right now. So let's actually go and calculate a Riemann sum. So we want to approximate the area R using a left Riemann sum with n equals 4 subintervals and illustrate this area. So I'm going to do a couple things here. The first thing I think I need to do if I'm looking at a Riemann sum is I need to figure out what do my subintervals look like. I need to figure out what are my subintervals. How small is each one of these pieces going to be? So in other words, I need to calculate what is delta x. Remember, delta x, that's the width of each subinterval, and we can find that using b minus a divided by n, just the length of the subinterval divided by how many pieces we want to cut that up into. So let's see, our interval we said was 0, 4. So I want 4 minus 0 divided by n is 4 subintervals. This is 4 over 4, which is 1. How convenient. So I'm going to sketch in this area just to see what it looks like here. So I'm going to sketch my region that we're looking at one more time. So, okay, here's our region. Perhaps it looks something like this. So, okay, we want to go from 0 to over here is 4. So I'm cutting this up into 4 subintervals. So when I cut this up, I'm going to say, okay, here's maybe 1 subinterval, here's 2, here's 3, here's 4. And each one of these subintervals should have the same width. Each one of those subintervals should have a length of 1. So let's actually go and start illustrating this area. I'm going to draw in the area and kind of do our calculations as we go. And actually, first, before I do that, I need to find the grid points here. We said each of these subintervals has length 1, so let me just label that here. Each one of these subintervals is length 1. So if I want to go from 0 to my next grid point, knowing that the subinterval length is 1, I just add 1 each time, so 0 to 1, 1, adding another 1 gets me 2, adding another 1 gets me 3, Adding another one gets me 4. So I want to create a left Riemann sum here. Let me do this in a different color. So I want a left Riemann sum. So I'm going to focus on this subinterval to start. I'm going to break this up into kind of 4 separate chunks here. First, I'm looking at the area between 0 and 1, keeping in mind we're using a left Riemann sum. So when I build my rectangle, I'm going to use the height of my function at the left endpoint, which in this case is 0. So I'm going to build a rectangle. I'm going to say here is the height of my function at 0. That is also going to be the height of my rectangle. Maybe I'll shade that in just a little bit. I'm going to find the area of that rectangle. So in this case, and actually how about we call this rectangle 1. So if I want to find the area of rectangle 1, so the area of rectangle 1, that's just the length times the width, or let's call it base times height here. The base is just 1. Your base is always just delta x. So I'm just going to call it delta x for right now, times the height of my rectangle. The height of my rectangle, well, this is the same as the height of my function, which, remember, my function is f of x. Actually, let's label it over here because I'm afraid I'm going to run out of room. We're working with f of x equals x squared plus 1. So the height of my function right here, we said we're using the height of my function at 0. So we're saying this is really f of 0 units tall. So I want delta x times f of 0. So don't overcomplicate this here. It is easy to overcomplicate this. This is the base times the height. That's all we're doing here. It's the base times the height. We do have some calculations to go and find now. So delta x, let me change my color. Delta x is 1 times f of 0. So I'm just going to plug 0 into my f of x function, x squared plus 1. So this will be 0 squared plus 1. So that gives me 1 times 1, which gives me 1. So the area of rectangle 1 is 1. I'm going to hold on to that thought for right now. We'll come back to that in just a second. Now I'm going to move on. Let's maybe do this in a different color. Let's do this in, oh boy, I don't want to use green here. Let's do, well, I guess we'll just do blue here for rectangle 2. So now I'm going to look at the subinterval between 1 and 2. So I'm looking at this subinterval. I'm going to call this rectangle 2. And I want for this particular subinterval, again, keeping in mind we're doing a left Riemann sum. So I'm going to use the left endpoint, which is 1, for the height of my rectangle. So I'm going to find the height of my function at 1, which is right here. I'm going to draw in my rectangle, and we're going to find the area of this blue rectangle that I've created. So the area of rectangle 2 then, again, I'm just using base times height here. So I would take delta x, which I'm just going to, well, we'll say delta x here, times f of, we said the height of this rectangle, we used 1. So I'm going to take this time 1 and plug that into my function. So this will be 1 times 1 squared plus 1. I have 1 times 2, which gives me 2. So the area of rectangle 2 is 2 units. And hopefully we're getting a feel for what this looks like now. Now we're going to move on to this area between 2 and 3. I'm going to call this one a rectangle 3. So we set it, okay, we're looking at the subinterval between 2 and 3, which means we want to use 2 to calculate the height of my rectangle. So I'm going to draw in that rectangle using the height of my function at 2 as the height of my rectangle. Say, okay, here is the area of rectangle 3. So if I want to find the area of rectangle 3, I'm going to take the height of my function, or actually, excuse me, I'll take the base first. The base is, of course, delta x. That part is never going to change. Our base is always delta x. Times f of, let's see, we said we were using 2 as the height of our function. So f of 2 here. So I have 1 times 2 squared plus 1. This gives me 1 times, this will be 5, this is 5. So the height of rectangle 3 is 5. And then I'll repeat it one last time. Now I'm looking at the subinterval between 3 and 4. I want to use the height of my rectangle at 3, or excuse me, the height of my function at 3 to determine the height of my rectangle. So I'll draw this in. I'll say, okay, here is the rectangle. I'm going to call this rectangle, oops, not rectangle 3, rectangle 4. So the area of rectangle 4 is again your base, which is still delta x, times the height of my function. We said we were using 3 to determine the height of our rectangle, so f of 3. So this would be 1 times f of 3. This would be, oops, 3 squared plus 1. So this is 1 times 10, which gives me 10. So if I want to approximate this Riemann sum, if I would like to find, okay, what is this yellow area that I'm now highlighting, kind of the area of all of the rectangles, I'm just going to add all of the areas that I just found together. So I'm going to take, let's see, we said 1 plus 2 plus 5 plus 10. And just add the results together. 1 plus 2 is 3, plus 5 is 18, plus 10, nope, 1 plus 2 is 3, plus 5 is 8, plus 10 was 18. I was just very excited to get to the answer. So 18, and we'll say we don't have a unit, so we'll say unit squared since we're talking about area. Here is our Riemann sum approximation. So this is really, really cool. I mean, it's a little bit tedious, but if you take your time and slowly think about it, you're just finding the area of each one of these rectangles, base times height, base times height, base times height, and then adding the results together. There are other ways you could kind of go about this. You could kind of add them together as you go, but I prefer this method. I think it kind of slows everything down and makes it a little bit easier to understand what it is exactly that we're doing. So that was fun. Now I want to do a right Riemann sum. I'm going to take that same function and I'm going to use a right Riemann sum. So okay, we're still using n equals 4 subintervals, which means that delta x is still 4 minus 0 over 4, which we said was 1. So we have the same partition that we had in the last example, in the last part. So we'll draw in our function one more time. So we say, okay, here's our function. I don't like that either. There we go. That's okay. So let's say here's 0 to 1, 1 to 2, 2 to 3, 3 to 4. So 1, 2, 3, 4. So this time the only difference between what we just did in part B and now in part C is we're doing a right Riemann sum. So how we calculate the area of these rectangles is going to be slightly different. We're just going to use the right endpoint to determine the height of our rectangle instead of the left endpoint. So if I look at my function here, let's say we're going from 0 to 1. So we're going to start right here, 0 to 1. I'm going to call this rectangle 1 once more. So if I want to find the area of rectangle 1, it's still delta x because the width of each one of these is still 1 on every single one of these. And now I need to figure out, well, what's the height? I have the base, what's the height? The height, so I'm going to look at, again, my subinterval between 0 and 1. I'm using 1 this time, though, as the height of my rectangle. So I'll say, here is the height of my function at 1. I'm going to use that to help me build a rectangle over this interval. So looks something like this, and I'm going to calculate this area. So in other words, I'm going to look at, well, what is this guy? That is f of 1 units tall. And remember our function, we said this is f of x equals x squared plus 1. So I want delta x times f of 1. So delta x, which is 1, times f of 1, that's 1 squared plus 1. We said that was 1 times 2, which gives me 2. And then I'm going to repeat that process essentially 3 more times. So now I'm going to look at, okay, let's look at this subinterval between 1 and 2. We're doing a right Riemann sum, which means I want to look at the height of my function at 2. That will determine the height of my rectangle. So, okay, here's the height of my function at 2. That's going to be how tall my rectangle is. Let's find the area of this blue rectangle, which I will call rectangle 2. So the area of rectangle 2 is, again, delta x, that's our base, times the height of our function at 2, so that is f of 2 units tall. So 1 times 2 squared plus 1, this is 1 times 5, which gives me 5. Next up, I've got the subinterval between 2 and 3 here, so I'm going to say, okay, we're going to use 3 this time, again, since we're doing a right Riemann sum. The height of my function at 3 to determine the height of my rectangle. So our rectangle will look something like this. So I will call this rectangle, oops, not rectangle 4, rectangle 3. So if I want to find the area of rectangle 3, it's the base, which is delta x, times the height. We said we were using the height of our function at 3, so times f of 3. So I will have 1 times f of 3. We said f of 3 was 3 squared plus 1. This is really 1 times 10, which would give me 10. One last subinterval to talk about. Now we're going to talk about this subinterval between 3 and 4. Here, again, we're doing a right Riemann sum, so I'm going to use the right endpoint, the height of my function at my right endpoint, to determine the height of my rectangle. So my rectangle looks something like this. I will call this rectangle 4. If I want to calculate the area of rectangle 4, its base, which is still delta x, times the height of my function at 4, so that is f of 4. So this is 1 times, let's see, 4 squared plus 1. This is 1 times 17, which gives me 17. So the last part of my Riemann sum, that word sum means add, so I'm going to add the results together. So I'm going to take 2 plus 5 plus 10 plus 17. So let's see, 2 plus 5, 7, plus 10 is 17, plus another 17, I should have 34 square units. Here is my right Riemann sum, is 34 square units. So cool, that's what a left and a right Riemann sum looks like. It can be a little bit tedious, but at the end of the day, we're finding the area of rectangles, we're adding them all up. The last question that I want to ask here then says, are these approximations overestimates or underestimates of the actual area? So let's go back and look at part B first. Are we overestimating or are we underestimating? I think that if you've been drawing your picture, if you have drawn in your Riemann sum, it should be pretty easy to see whether we're overestimating or underestimating. Here, there's all this area under the curve that I'm shading in now, in green, that I didn't count. So that means that this was an underestimate. Because the area that I found is actually less than the area that I wanted. I wanted the full region R, and I have these little sections that I'm not counting. So this is an underestimate. In this example, I have the opposite problem. Each one of these rectangles is a little bit too big. It's going over the function. I'm actually counting a little bit too much area here. So this is an example of what an overestimate looks like. So be careful. The one thing I will leave you with here is that left Riemann sums will not always necessarily be underestimates. It just works out that way because this is an increasing function. If you had, say, a decreasing function, and I'll actually draw that in. If I had a decreasing function, something that looks like this, if you were to draw in a left sum, you would actually be overestimating here. So we can't necessarily just assume that a left sum is always going to be an underestimate and a right sum is always going to be an overestimate. You have to actually look at your function, determine whether it's increasing or decreasing, or draw the picture in order to see, do we have this area that's perhaps a little bit over what we want, or is there perhaps some area that we're not counting that we need to kind of compensate for. So just be careful. You make sure you look at your picture before you decide whether your estimate is too high or too low.